Hello everyone and welcome back. So last time we had a video on this problem. That is the method of the infinite descent. Now we also had a question from a viewer about whether descent is an exhaustive algorithm that could miss a solution. The short answer, it is an exhaustive proof because it shows solutions are simply impossible. And today, we're going to see Fermat's genius on full display as we use that exact method, the infinite descent, to tackle his most famous equation for the special case of n equal to 4. This is a remake of the video in a new format. So this lecture will start with a quick refresh on how primitive Pythagorean triples are parameterized, and then we'll jump into the full two-part descent argument. Our target is actually the stronger statement that the equation here is x to the fourth plus y to the fourth equal z squared has no integer solution. Why that is stronger? Because z4 is simply some squares squared. Basically, we're trying to prove the stronger statement here. Let's go right into this two parts lecture.
Right now, in the n equals 4 proof, we are assuming, for contradiction, that there is a primitive integer solution to x to the fourth plus y to the fourth equals z to the fourth. We then look at the right triangle whose sides are x squared, y squared, and z squared. Because the original solution is primitive, this new Pythagorean triple with sides x squared, y squared, z squared is also primitive, and exactly one of x squared or y squared is even. We agree to call the even leg x squared, and we parameterize this primitive right triangle using integers m bigger than n.
So this is the usual Pythagorean triple setup, but now applied to x squared, y squared, z squared, with x squared chosen to be the even leg?
Exactly. And the key reminder is that for a primitive triple, we choose m and n with greatest common divisor 1 and of opposite parity, meaning one is even and the other is odd. Without those conditions, the triple we get would not actually be primitive or would have both legs even, which would break the argument. Here is the concrete formula we rely on in the descent. For a primitive right triangle whose even leg is x squared, we can write x squared as 2mn, the other leg y squared as m squared minus n squared, and the hypotenuse z squared as m squared plus n squared. We assume m and n are positive integers with m greater than n. They share no common factor, and one of them is even while the other is odd.
Why does the even leg have to look like 2 times m times n specifically?
Because in a primitive triple, the two legs cannot both be odd. If you look at the standard algebraic derivation, you express the hypotenuse plus the odd leg and the hypotenuse minus the odd leg as two factors that multiply to the even leg. Those two factors turn out to be coprime and of the same parity, so each must be a perfect square. That forces the even leg to be twice a product of two coprime integers, which we call m and n, giving x squared equals 2mn, and the rest of the formula follows. Now, why does this description capture exactly the primitive triples with an even leg? First, start from m and n that satisfy the condition shown. Plugging into the formula gives a triple with legs 2mn and m squared minus n squared, and hypotenuse m squared plus n squared. Any common factor of m and n would divide both m and n, and therefore divide all three side formulas. So insisting that m and n are coprime ensures the triple is primitive. And because one of m or n is even and the other is odd, exactly one leg comes out even.
So if we pick, say, m equals 2 and n equals 1, that should give the classic 3, 4, 5 triangle in this scheme?
Right. With m equal to 2 and n equal to 1, 2m, n is 4, m squared minus n squared is 3, and m squared plus n squared is 5. So we recover the 3, 4, 5 triangle in the order 4, 3, 5 with the even leg first. Conversely, starting from any primitive triple with an even leg, you reverse the same factorization argument. You look at the hypotenuse plus the odd leg and the hypotenuse minus the odd leg, show that those two numbers are coprime and have the same parity. and conclude that they must be squares of m and n. That recovers m and n and brings you back to this parametrization. Here's a quick exit check. Pause for a moment and see if you can state from memory how x squared, y squared, and z squared are written in terms of m and n for a primitive right triangle whose even leg is x squared. Then recall in one sentence why the primitiveness forces m and n to be coprime and of opposite parity.
So we should get x squared as 2mn, y squared as m squared minus n squared, z squared as m squared plus n squared. With m and n positive, m bigger than n, no common factor, and one of them even and the other odd.
On this slide, I am reminding you of the headline version of Fermat's last theorem. It says that there are no non-zero integers x, y, z. Solving x to the n plus y to the n equals z to the n once n is at least 3. We are going to zoom in on the case n equals 4, and in fact we will prove something even stronger, that there is no integer solution at all to the equation x to the 4th plus y to the 4th equals z squared. If that stronger statement is true, then it automatically rules out x to the 4th plus y to the 4th equals z to the 4th, because a 4th power is itself a square.
So proving the square version is actually enough for the n equals 4 case of Fermat's theorem?
Exactly. Think of z to the 4th as just another square, namely z squared squared. Any solution to the n equals 4 equation would give a solution to the square equation, so ruling out the square equation is the more powerful statement. Now let us outline the strategy. Our target equation is the one at the top. X to the 4th plus y to the 4th equals z squared. If we group the exponents differently, it says that x squared and y squared are the legs of a right triangle whose hypotenuse is z. That means we can use the classification of primitive Pythagorean triples that you have seen before. The other big idea is called infinite descent. We will assume there is a solution with the smallest possible positive z. Then we will use Pythagorean triples twice to manufacture a second solution with a strictly smaller z. That cannot go on forever, so the original assumption must have been wrong.
When you say infinite descent, you mean we would get a never-ending sequence of smaller and smaller z values, all positive integers?
Yes. Picture an infinite staircase going down but never reaching 0. That cannot exist for whole numbers, because you cannot keep subtracting at least one forever and stay positive. So producing even one strict step down is enough to get a contradiction. To start the descent, we suppose there is at least one non-trivial solution in integers x, y, z, with x to the 4th plus y to the 4th equal to z squared. Among all such solutions, choose one where z is as small as possible and also positive. If x, y, and z had a common factor bigger than 1, we could divide it out and get a smaller z, contradicting minimality. So we may assume the triple is primitive, meaning the greatest common divisor of x, y, and z is 1. We can also swap x and y if needed, so that x is even and y is odd. That ensures that x squared, y squared, and z form a primitive Pythagorean triple.
Why is it important that the triple with x squared and y squared be primitive?
Because the clean parameter formulas for right triangles only hold in that primitive case. If we know our triangle is primitive, we can write x squared, y squared, and z in terms of two new integers m and n with very strong conditions, and those conditions will let us force certain numbers to be perfect squares later on. Since x squared, y squared, and z make a primitive right triangle, we can use the standard parametrization. We take m and n to be positive integers with m greater than n coprime to each other and of opposite parity. Then the even leg of the triangle is twice mn, the odd leg is m squared minus n squared, and the hypotenuse is m squared plus n squared. We arrange things so that x is even, so x squared is the even leg. That gives x squared equals 2mn, y squared equals m squared minus n squared, and z equals m squared plus n squared. All of the number theoretic information about x, y, and z is now encoded in the simpler pair m and n.
How do we know that m and n really are coprime and of opposite parity here?
That is a standard theorem about primitive Pythagorean triples. If a and b and c are primitive with a squared plus b squared equals c squared and a even, then there exists coprime m and n of opposite parity with exactly this form. We are simply applying that theorem with a equal to x squared and b equal to y squared. Next, look at the expression for y squared. It is m squared minus n squared. Rearranging, we get y squared plus n squared equals m squared. So y, n, and m themselves form the size of another right triangle, this time with y as an odd leg, n as an even leg, and m as the hypotenuse. One can check that y and n are still coprime, so this smaller triangle is also primitive. That means we can apply the Pythagorean triple formulas again, now introducing two new integers, r and s. With r greater than s, coprime, and of opposite parity, we have y equal to r squared minus s squared, n equal to 2rs, and m equal to r squared plus s squared.
Why should y and n be coprime? Could they share a factor that we have missed?
If a prime divided both y and n, then looking back at the equations for x squared and y squared in terms of m and n, that same prime would have to divide x as well, and then also z. That would contradict the fact that x, y, and z have no common factor. So y and n must be coprime, and the second triangle is primitive. Now we start to force some of these parameters to be perfect squares. First, notice that n is even because n equals 2rs. So we can write n as 2k for some integer k. Go back to the equation x squared equals 2mn. Substituting n equals 2k, we get x squared equals 4mk. Or, equivalently, x over 2 squared equals m times k. From the construction of the first triangle, we know that m and n, and hence m and k, are coprime. So we have a product of two coprime integers, m and k, that is a perfect square. That is only possible if m and k are themselves perfect squares. On the other hand, in the second triangle, we also have n equals 2rs. Combining n equals 2k and n equals 2rs shows that k equals rs. Substituting into the equation for x over 2 squared gives x over 2 squared equals rs times r squared plus s squared.
Can you remind me why a product of two coprime numbers being a square forces each one to be a square?
Think about prime factorization. In a perfect square, every prime appears with an even exponent. If a and b are coprime and their product has only even exponents, then each prime can live in only one of them, so all the exponents in a and in b are already even. That means both a and b are squares on their own. Now look carefully at the factorization of x over 2 squared. It is r times s times r squared plus s squared. From the Pythagorean triple theory, we know that r and s are coprime. And a short check shows that r squared plus s squared is also coprime to both r and s. So we have three pairwise coprime factors whose product is a perfect square. By the same prime factor argument as before, each of these three factors must itself be a perfect square. So we can write r equals x0 squared, s equals y0 squared, and therefore r squared plus s squared equals z0 squared for some integers x0, y0, and z0. But then r squared plus s squared equals z0 squared says exactly that. X0 to the fourth plus y0 to the fourth equals z0 squared. So we have manufactured a new solution of the same shape as the original one.
And this new z0 really is smaller than our original z, right?
Yes. Remember that m from the first triangle equals r squared plus s squared, which now is z0 squared. And the original z equals m squared plus n squared, which is bigger than m, hence bigger than z0 squared, hence bigger than z0. So z0 is a strictly smaller positive integer than z. Let us put the pieces together. We began by assuming that there was at least one solution with x to the fourth plus y to the fourth equal to z squared, and we chose one with the smallest possible positive z. From that single solution, we have just built another solution with new numbers x0, y0, and z0, such that z0 is strictly less than z. But we can now repeat exactly the same reasoning starting from this new solution and obtain yet another one with an even smaller z1, and so on. This would give an infinite chain of strictly decreasing positive integers, z greater than z, 0 greater than z1, and so forth, which cannot exist.
So the only way to avoid that impossible infinite descent is that our very first assumption was wrong, and there was never any solution to begin with?
Precisely. There is no non-trivial integer solution to x to the fourth plus y to the fourth equals z squared. And because a fourth power is a square, this immediately implies that there is also no solution to x to the fourth plus y to the fourth equals z to the fourth, finishing Fermat's theorem in the exponent 4 case. To solidify the key lemma we used, look at the equation on this slide. Suppose a and b are coprime and their product equals the square t squared. Using the prime factor point of view, try to convince yourself that both a and b must themselves be perfect squares. That is exactly the reasoning we applied twice in the proof. First to m and k, and then to the three factors r, s, and r squared plus s squared.
So the answer is that a and b each have to be squares, because otherwise some prime would appear to an odd power in one of them, and then to an odd power in the product too?
Yes, that is the idea. For reflection, think about where the primitivity assumptions were crucial. We needed the greatest common divisor conditions to know our factors were coprime, and without that, we could not force them to be squares. Also, notice how infinite descent feels like reverse induction. Instead of proving that all large numbers work, we show that even one example would drag us down forever, which is impossible.
Thank you for your time in watching this. Please like, share, and subscribe to the channel. Of course, we always would like to hear from you. Please make your comments below.